So kind of going over Br2 as a reagent. What different ways have we been using it? So the first way we learned was just Br2 with an alkene. And this is when we made the bromonium ion, we did the dibromination, right? Transaddition. We put 2 bromines on. What I've subsequently shown you is with Br2 and light, or with the same alkene and something called NBS in light, which is NBS is basically a way to get to a low concentration of Br2. Because the problem with Br2, if you have any Br2 around, right? So in this case, we need the light to react with Br2 first to make the 2 Br dots. But let's just say, right, if the Br2 is around the light and that reaction doesn't take place first, where the Br breaks up into Br dots, this Br is just going to behave like it is up here. So it's helpful to be able to have Br2 in low concentrations and still do these radical reactions. So that's why when they said in the homework, when it said, you know, what do they mean by low concentrations? They meant low concentrations because if you had a lot of Br2 around, like that would be like this case up here, and then you'd add 2 bromines, and you didn't want to do that. You wanted to get the allylic position activated and do a substitution there. So that's what the low concentration was all about. So MBS is a way to get a low concentration of Br2 without having to do the dibromination then. Right? So that was the whole idea there. So there's 3 ways to use Br2.
So essentially the Br2 and HB and NBS and light will do the same thing?
Do the same thing. That's right.
Can we go over the mechanism for those?
Yes. So the Br2 mechanism, Br2 in light is different than the NBS mechanism. So Br2 in light always goes for the weakest CH bond to break, right? And an allylic CH is weak because you make a allylic radical, which you can stabilize with resonance. Right? So let's take a look at one of those. So let's see. Let's say something like this, and we're going to react it with Br2 in light. All right. So the first step is an initiation, and that's where, right, the bromine essentially becomes 2 Br dots. Right? Initiating the radical species that we need to react, right? The one we're actually going to add. Now, propagation step here, and now we're actually going to react with this. If you see Br2 in light, you should think, what is the most stable radical I can make? Right? So if I number my carbons, 1, 2, 3, 4, 5, 6, 7, you should automatically realize you're not going to react with the pi bond. Right? Because that would be just like reacting Br2 without light. You don't want to do that. So you're going to go for the allylic positions. The allylic CHs, that's what you're going to eventually substitute. Now this is going to be a little more complicated because there's going to be some resonance forms here. Right? So which position is the allylic position? What H on which carbon that I have numbered here are we going to attack?
6.
Why 6? Because it's more substituted and still the allylic. Right? How many allylic positions are there? 2. Carbon 6 is allylic, carbon 1 is allylic. But isn't carbon 4 allylic too?
Can it be?
It's not allylic,
Yeah.
right? Allylic means it can't be sp2 hybridized. It really has to be sp3 hybridized. So it's 1 or 6, and we've chosen 6 because that's secondary. You make a secondary radical. Secondary radicals, more stable, hyperconjugation. All right, so let's draw that out. We'll draw the mechanism out here. So we're going to say this is going to find a Br dot. The CH bond is going to break. Now this is a propagation step. That means we need to generate a new radical from this. And we also made HBr. Now there's going to be some issues though, because now we've made this radical, it's very similar to a carbocation. What can radicals do just like carbocations? So it's not really rearranging as much as it's able to do resonance, right? Because remember, radicals can't do hydride and methyl shifts, right? But they do resonance, right? So it looks like it's a rearranged product, right? We're not just gonna get the bromine on carbon 6. We're gonna see some other rearrangements or resonance forms. So here we go. So I would draw this out at least once, right? When you see a radical intermediate like this, you should probably say, I better draw it out a couple times, right? So let's just draw the easy one. I'll redraw this again. So the easiest one we know, what's the path of least resistance here? What's the easiest thing that's going to happen? Is that we're going to do a termination step, and that our new radical is going to find what? Another Br dot, right? That would be the easiest thing to happen. Whoops.
So if we put that answer on the test, would that be wrong?
It's not wrong, it's just not all the answers. It's not all the possibilities.
So would you say give me all the possibilities?
I would probably say give me all the possibilities. Give me draw all the possible intermediates and give me all the possible products.
Oh.
And then remember we talked about in class about thermodynamics and kinetics, and maybe draw a free energy diagram, something like that as well. All right, so let's do some resonance forms now. So I redrew this the same exact intermediate because I don't want to have, right? I can't have this. If this is reacting this way, I can't have the resonance structure going at the same time in the same molecule. All right, so to redraw it, we'll number our carbons again. All right, there you go. Do some resonance here. There's 2 electrons in this pi bond. One's going to carbon 4. One's going there. So where's our new pi bond at? Between 5 and 6. And who has the radical now? Carbon 4 does. Very good. Can I do another resonance structure? Okay, can. So let's move this up. I'm going to redraw this guy. So if this was the first one I drew, if it was to react with Br dot, where would the bromine end up on? Carbon 4, right? So here's one product. I'm just going to erase this and draw this as the product down here. That was a bromine on 4. That's another product. But like we said, I think we draw another resonance form here, so let's redraw that intermediate. So I'm taking this guy back over here. One, two, three, 4, 6, 7. All right. Draw a resonance structure with this one. 1 electron going there. Where's there a new pi bond at? between 3 and 4. Radicals now on 2. Three, 4, 5, 6, 7. And now, of course, bromine could react over here. Now they would come together. And that would give us Br there. One, 2, 3, 4, 5, 6, 7. Give us another product. Now I think, if I take a look here, that's all the resonance forms you can draw. I think that's the third and the first one are pretty similar, if not exactly the same. There's some differences in like cis trans double bonds, but I wouldn't take you to that level of, you know, they'll probably all be trans, right? If double bond, if alkenes could be trans, they will be, right? So I think 1 and 3 are basically the same molecule, but aren't they? Yeah. But so there's really 2 types of products you'd form here. But I'd want to see the intermediates draw the resonance forms and those kind of things. So an interesting question should be here, what product, so there's 2 types of products, right? If I label these, this is A, this is also A, and this is B. So who has the more stable intermediate?
B.
Why B? I don't think the intermediates, I actually think A would have a more stable intermediate. This would be a more stable intermediate. Because they're both secondary, right? Both secondary. What's better about A's intermediate than B's? It's conjugated. So which product do you think is more stable, A or B?
It's definitely A.
Definitely A. So actually A comes from the most stable intermediate and the most stable product. So it would be both the kinetic and the thermodynamic product. It comes from the most stable intermediate and it is the most stable product, right? So it actually is both the kinetic and thermodynamic product. So it'd be really hard to form B.
So for the product, because A is the thermodynamic product, whatever, or the best product, is because of the conjugation.
Right. Conjugation is the same deal, why A is more stable. So yeah, it's one of those situations where, right, and it happens a lot where both the most stable product and the most stable intermediate and the most stable product are one and the same. Not happened here, so that's A as well. Good question. All right, let's do one where we can get this the anti-Markovnikov product, right? So we knew the anti-Markovnikov product with BH3, and we got the OH on the less substituted carbon, right? So anti-Markovnikov product means the new functional group always ends up on the less substituted carbon. So we have a way to do that now with these bromines. So if I have HBr and peroxides, the product I get is the anti-Markovnikov product. The bromine ends up on the less substituted carbon of the alkene. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So this mechanism is a little different. Same type of steps, though, right? Initiation, propagation, termination. So step 1 is initiation. Now remember, we're adding a bromine. So until we make Br dot, we're not done doing initiations. Until you make Br dot, you're not done. So let's see. So the first step, let's go for the weakest bond. And the weirdest looking bond here is the ROOR bond, I think. Peroxide. So let's break that with some light, or just kind of breaks itself. They're not real strong bonds. So now we got 2 RO dots. But like I said, we're not adding RO dot. We're adding BR dot. So until we've made BR dot, we have not finished initiating. So, and one of the RO dots, not 2 of them, just one. An RO dot is going to react with HBr, the next weakest bond. Now, we've made an alcohol, and we've made a BR dot. Now this BR dot's gonna react a little differently than the ones we've seen in the past. Right? So it's not gonna be like MBS, and it's not gonna be like BR2 in light. It's gonna be a little different. And it's gonna react, so a propagation step is gonna react with the carbon molecule, our start material, but it's gonna react with the alkene. Right? It's gonna react with the alkene. The key here to remember is, what kind of radical do you want to form always? If you had a choice, right, if I numbered these carbons, 1, 2, oh, wrong way. Right, if I numbered the right way, 1, 2, 3, 4, 5, 2 or 4, where do you want to have the radical at? Carbon 2 or carbon 4? Why? It's more substitute. That's a fact. But why was that better? As you're more substitute, you have more hyperconjugation, right? Don't forget, right? A why question is not if you say it's more substitute, that's a fact. That's not a why, right? That's a fact, right? So hyperconjugation is why it's more stable. Because it's more substitute is why it has more hyperconjugation, right? So we're in the situation now where, okay, well here comes BR dot, and we're going to break this pi bond. So where do we want the bromine to actually, where do we want the radical to end up? Which carbon? 2. So let's have it go to 2. So then where's the bromine going to have to end up? Carbon 4. The less substituted one, right? Good? So we're close. So to this point we can say, oh, we need to get an H on there, right? Because net, what kind of reaction is this net? What kind of reaction are we doing from here to here? It's an addition reaction, right? We're adding H and Br across this pi bond, right? Not a substitution, right? Are we changing any elements here? But we're adding, we're doing an addition. So the last step, to get the final product, we know we need to add an H there, right? To carbon 2.
Is this a termination step or?
Well, let's see. So another point of confusion is, just because it's a termination step doesn't mean it's a product forming step. Right? Termination means when two radicals come together and they don't form any radicals. Right? So just because it's a termination step doesn't mean it's a product forming step. But we know, what do we need to get on that carbon 2? An H. We got to find something that has an H. Well, HBr is around. Let's use that. So what's the net of this reaction? Is it a propagation or a termination or an initiation? This reaction I showed here.
Still a propagation.
Why? Why is it a propagation? What radical did I form? You made another BR dot, right? It's a propagation. New H bond there, plus BR dot. 1, 2, 3, 4, 5. So we're not done. But we are done making the thing we want, right? This is the product. This is the major product. Right? But we're not done. So at this point, there's lots of different ways. You can take any two radicals, right? You can take this and BR dot, and that would be a termination step. You can take two BR dots, and that would be a termination step. You can take an RO dot and a BR dot, and that could be a termination step. You can take an RO dot and this carbon thing, and that could be a termination step. So there's plenty of options for termination steps, but they're not really the ones that, in this case, are forming the product. Right? So usually these reactions keep going until we stop them, right? Till we quench them. So the termination, right? Termination just means exactly what it sounds. The reaction is over once it terminates. But that doesn't usually happen in these until we want it to happen. So really thinking about, right, what's the likelihood that two BR dots find each other? Not very good. Right? Because those break again. Right? So once we form something like this doesn't really react anymore. It kind of stops. Right? So you still have terminations here, but they're just not that likely. Versus the other one, which was much more likely. So just because the termination step doesn't mean it's the product forming step. That's the big take home message. But everybody see what kind of termination steps you could have here?
I have two questions.
Yes.
Where did that second HBR come from? Is it just a?
Yep, so HBR is probably just a little bit extra HBR around, so that's probably where that second HBR just came from.
Okay.
And you have another molecule of it.
And then for termination steps, are you gonna ask us like,
Show me one example.
okay, so it's not gonna be like, try to find all of them?
No. I could never ask you to try to find all of them. I could show you a product and say what draw the starting materials from this here's a termination step product. What two star materials did it come from? Or I could say, give me one example of a termination step. Something like that. So I'm going to take number 8 from the 2014 exam 3. And I'm going to turn it actually into a free energy diagram. So I'm just going to draw the mechanism. This is with H2SO4, which of course everyone knows how to draw. Should put that as a question on the test. Should it be 4 credit, not extra credit. Extra credit questions are bonus questions. That's make a bond, break a bond. Just take a strong acid, H2SO4 is a strong acid. Get to
Do you put a lot of carbons on it just to be obnoxious?
nope. There's a reason. You'll see.
Valid question.
So what kind of alkyl leaving group do we have? Primary. All right, there it is. So we can either do what are two possibilities? The primary alkyl leaving group. What are the possibilities? E2 or SN2. But now we look at our we have a sulfuric acid anion. So is that going to be a nucleophile or a base? Base. So let me just number these 3 guys. So where's the H at that I'm taking away that to remove this for this E2 reaction we're going to do? So which carbon is that? Beta hydrogen. So which carbon? Carbon 2.
Why do we go at carbon 2?
That is because we're doing an E2 elimination. So where is the pi star or sigma star is on 3, and so we need to have these guys lined up anti-periplanar to do that elimination. So now most people would say, hooray, I'm done. Why are you not done?
Because you still have H plus and that can
What can H plus do?
attack.
Will it react with an alkene?
Yeah.
Yes, it will. Old school.
So this is the E2 to E1 one.
Yep, we did E2. And now we got a carbocation there, but now it's a secondary carbocation, so that's okay. We remade our anion. So now where are the beta carbons, or the beta hydrogens, where are they at? So yeah, why did you pick carbon, which carbon are you going to pick?
Carbon 1.
Carbon 1. Why?
Because it's more stable because of what do you call it? It's a benzylic. It's because of its position.
So it's a benzoic position, but why? So why is that? But still going to be.
Because you'll have it more substituted.
Not only will I have it more substituted,
You'll have the
I'll also have the conjugation to the benzene ring, right? It's right next to the benzene ring, right? I didn't draw it this way, but you guys should recognize. Right, there's pi bonds in there. Putting pi bonds next to each other, conjugation, that's a good thing. So it's a double whammy here. But this is definitely an E1 reaction, right? The first one had to be an E2. This was an E1. And so where did our pi bond end up? Okay, 1 and 2. I'm drawing it trans because, right, trans, it makes more sense. 1, 2, 3. Good. Good. So let's label these. So we'll call this, so are these intermediates, transition states? What are these? All these things I have right here, what are they? All these, this, and this. What are they? Well, not this. This is the end. That's the product, right? This is the start material. But what are these three things? Transition states or intermediates? They're all intermediates. If they're intermediates, where are they at? Top of the hill or in a valley? Right. Let's remember. Let's not mess that up again. Right. I saw a lot of intermediates at tops of hills. I saw intermediates we forgot. Right. You drew it in a mechanism and then it never showed up in the free energy diagram. Right. If it's in the mechanism, it's got to be in the free energy diagram. Right. So let's label these guys. So let's say we'll call this guy IA for intermediate A. IB for IC for C, and then prod for prod. Yep, product. And then this, of course, would be start material. So let's look at first we'll do these by energy, and then we'll make the free energy diagram on another slide. So let's talk through these. So start material and product, I don't really know. I mean, maybe you could say the product's more stable than start material. I'm not really worried about that. But let's compare the intermediates. What intermediate is the highest in energy? Right, so whenever you get a thing, we have to rank things, right? I always think find the extremes, right? Work from the extremes. So let's say which one's the highest energy, or which one's the most stable? Which one do you guys want to do? Most stable or least stable? Which one's the most stable by far? IB is by far the most. Not by far, but IB is the most stable, right? IB is the most stable. All right. So if I said IB is more stable, most stable. What's the least stable? Why IC? Carbocation, no full octet. Boom. And then where must IA fall? Somewhere in between. Now, not only that, but how much worse is IC than the other two? A lot worse, right? So this is one time where, right, you might want to show your free energy diagram IC being much higher in energy to show or at least say, hey, this has no full octet. I know this is really high in energy, right? I don't draw good either. Well, whatever, right? So hopefully somebody remembers the rankings. Starting material, there she is. Maybe we'll say the product is lower energy because of conjugation. Yay. The first thing we went through is IA. So let's put, IA is not bad, right? Still has a plus charge, but not bad, right? That was that first, the alcohol gets protonated, right? And that's probably going to take, a little bit of energy. And there's our transition state. Now IB was the alkene, right? So I'm guessing IB, we're down here almost the same level as the starting material probably. Right? That's no charge, that's a stable product. Down we go. Little transition state. But now where the heck is IC at?
Way up there.
Way up there. It's probably up here. And that's a carbocation. That's going to take some juice. Up we go. Transition state. And then finally deck down to our product. So that's how I would do that's how I would do the free energy diagram for number 8 in that test, in the old exam from 2014. Let's take a look at,
Do something with Tassel.
I'm gonna do one without Tassel. I'm gonna do it with this. I'm gonna have it react with, oops, not that. Secondary alcohol reacting with PBr3. Right? And I do need to have pyridine, right? I do need some pyridine. Got some pyridine in there. First step is the alcohol. It needs to get activated. It's going to attack the delta plus fluorine or phosphorus. So you gotta be kind of
Anything, or are you making this up?
making this up. So kind of gotta be careful here. You notice the starting material is a secondary alcohol, and it was an asymmetric center. There's 4 different things bonded there. So it was, let's say, 1, 2, 3. It is S. And so it's starting out as S. And if you see PBr3 or zinc Cl2, PCl3 or SOCl2, you should look at those and say, hey, I know that within their activation mechanism there is an SN2 step. So at the end, you should know. You should say, I know I'm adding a bromine, and I know the final product should be R. So one of the things you could do, right? So you should be able to recognize these and just draw the product right away before you even draw the mechanism. So let's just do that. Who can draw the product right away? And that way we even know where we're trying to go. So what is the final product going to look like? So it has to be R. So the easiest way I would do it right? Because I know if this is coming out, the bromine's of course going to attack from the back side, and as that attack happens, the H comes forward, right? And now we should double check ourselves, right? So bromine's ranked 1, 1, 2, 3, but the H is coming out, so this is is R, right? You can always bring your model kits. Always bring your model kits. Totally can use your model kits. Nothing wrong with that. And so it is indeed R. So that's now we know where we're going, right? That's helpful, right? So let's see. Finishing off what we got started here. PBr2 is on there, and we lost a Br minus, and we said the pyridine is of course floating around. So I'm going to do it. The pyridine takes the H first. It doesn't matter if you want to do it this order or not. You could have the Br minus attack the carbon first. It's up to you. We also should know the other byproduct here is this plus, let's see, there's O, balance my charge. What's the other thing? Is it O minus? Yes, it is. O minus PBr2, right? To balance everything out, the byproducts. So after the pyridine takes that H, still have that. I have the O attached to the phosphorus, Br2. I have a pyridine now with an H on it with a plus charge. Now we had to balance our charge. There's a Br minus still. All right, we start out with, was there any charge in the beginning? No. So if I have a plus charge, then I have to have a minus charge, right? I have to balance it out. I have to overall no net charge. Don't want to lose carbon. All right. So the last step here is there's this SN2, and that leads us to these guys. Okay, a couple examples about how PCC and NaOCl, the bleach, react. So the biggest thing these guys do is they take 1 alpha H, right? 1 H from an alpha carbon. So, what if I showed you this? Or if I showed you this? What would these have come from, and what reagents are possible here? So if I label these B, C, and A, for A, what's the starting material? Secondary alcohol. Good. For B, what's the starting material?
Primary.
It's a primary alcohol. For C, what's the starting material? Also primary alcohol. Okay. For C, what reagents can I use to get that transformation, to go from alcohol to aldehyde? PCC or the NaOCl, right? That would work. For B, what reagent do I need to use to go from a primary alcohol to carboxylic acid? Chromium, right? And you use the I need to use the chromium. Right? Chromium, remember, takes more than one alpha CH. It'll take all of them, right? But what about A? What reagents can I use for A?
CR07.
I could use chromium. I could use PCC,
Yep.
or I could use NaOCl. I could use all of them, right? Because how many alpha CHs are changing in A? How many am I losing? How many alpha CHs am I losing?
This one.
Just the one, right? There's just one here, right? So all of these would work on that one. Would any of them work on a tertiary? No. If you don't have any alpha CHs, you can't do an oxidation. Good. So let's do a problem with Tassel. So let's say we have a tertiary alcohol, we have a secondary alcohol, and we have a primary alcohol. I'm going to say the first step is Tassel chloride in pyridine, and then we're going to add in, we'll add in this, that's step 2. Here we'll have, by God, I'll do the same reagents for all of them. Make this really easy. Pyridine 2, there's that guy. Step 1, Tassel chloride in pyridine, Cl, pyridine 2, methoxide. What are going to be the final products for all of these? Okay, so I will draw after the first step what we get, right? This is a classic example. Make sure, right, if it says step 1 and step 2, right, if it's underneath the arrow and it says step 2, that's a completely different step. Do not mix steps 1 and 2 together, right? These are reagents, they react with the starting material. So I'll draw the first product for each of these. This is after the first step. So after step 2, what's going to happen? So we look at all of these, and we should ask ourselves, what kind of alkyl leaving group do we have, right? That is what dictates everything. That's the first question we ask ourselves all the way through SN1, SN2, E1, and E2, right? What type of alkyl leaving group or what kind of leaving group do we have? So what kind of alkyl leaving group do we have in the first one? Tertiary. So that should automatically eliminate something. What does that automatically eliminate? SN2. Perfect. And the next one, what kind of alkyl leaving group do we have? Secondary. And the third one, what kind of alkyl leaving group do we have? Primary. Good. Now we take a look at our, right, so now we're down to, right, for the top one, we said no SN2, right? So it's either E2, E1, or SN1. So now let's look at our nucleophile base and take a look at it. Is this nucleophile base reactive or not reactive? So then what is it going to be? So it has to be E2, right? A reactive base or nucleophile is either SN2 or E2, and we've already eliminated SN2, so it's going to have to be E2. So the product is going to be an elimination, an E2 elimination. That's it. Now let's go down to the primary one. So the primary, we know it can't be SN1 or E1, right? Not possible. So what's left? E2 and SN2, right? So E2 and SN2 are left. So between E2 or SN2, up here of course was E2, that was the winner. So between E2 and SN2, we look at our nucleophile base. Is it reactive? Yes. Okay, that has a note. Is it big or small? Small, so it's going to be SN2. Fair? Now let's go to secondary. What's possible for this? So O-Tassel is our leaving group. Can we do SN1 or E1? Are we going to form a secondary carbocation? Why not? It's not a good enough leaving group. This is not a good enough leaving group. So what's left? SN2 or E2. And we look at our base or nucleophile. Is it reactive? Yes. Is it large or is it big or small? So what's more likely? SN2 again is more likely. Right, there's factors that we can force to get E2, right? If there's conjugation maybe, but this case it doesn't have it. So we do the SN2. That's how Tassel can kind of be exploited, right? Those other ones, right? The other four methods, the zinc Cl2, PBr3, PCl3, SlCl2, they don't react with tertiary, right, alcohols because we can never do that SN2 step that they need to work.
How did we use E2 on a tertiary?
Because we make a more substituted alkene, we absolutely can do E2 on tertiary. We never can do SN2, right? Because sigma star is blocked. So E2 is really actually more likely. Yes.
What happens, like, will the chlorine just never react with anything?
Yeah, not with Tassel. Remember with Tassel, the chlorine doesn't come back around. Right? Tassel just stays on. Yep.
Doesn't the chlorine form a salt with the, there is?
Right, yeah, it would form, I didn't draw all the products, right? I didn't draw the chlorine salts and all those kind of things. I didn't draw the alcohol that we'd form here. But yeah, absolutely, it's still formed. I was just showing the major parts that we look for.